Hey guys, so this is section 9.4 where we talk about the temperature composition diagram and fractional distillation. In the previous section we looked at the PZ diagram, pressure versus the average composition. It ends up that it's convenient to look at the TZ or temperature composition diagram when we're talking about distillation. And so to look at the temperature composition diagram, we fix the pressure, and it ends up being really convenient if we choose that pressure to be 1 atmosphere, because then at 1 atmosphere the boiling point will be the normal boiling point, which it's easy to look up and useful. So one thing to notice about this is compared to the PZ diagram, this is inverted, and that's because as the mole fraction of the more volatile component, in this case benzene, by the way this is the same solution, benzene toluene. But benzene has a higher vapor pressure, lower boiling point than toluene does. As we get more and more benzene in the mixture, the boiling point of the solution decreases. So it goes in the opposite direction of the PZ diagram. So this curve right here is the boiling point of, as a function rather, of the mole fraction of benzene in the gas phase. This is the boiling point as a function of the mole fraction of benzene in the liquid phase. Notice neither one of these guys are linear. Now we can look at distillation here, the process of distillation, if we imagine following this path from A, B, C, D, and so on. So the idea is we start with the liquid, raise the temperature up until we get to the boiling point of the liquid as a function of the mole fraction. And at this temperature right here, the more volatile component will vaporize, and we'll get a vapor up here. And then when we get over here, we lower the temperature, and so we have a different mole fraction. We have more of the more volatile component here, and then at that temperature we heat it up until this happens. At that point we cool down the temperature, so we have more of the more volatile component. Do that again and keep going and going and going, and each step we increase the mole fraction of the more volatile component. Because see, what happens is here we boil it, the liquid, the solution stays behind. There's some A and some B, some benzene and some toluene. Here there's more. This is more rich in the lower boiling point component than in the higher boiling point component. In this case, this vapor will have more benzene than toluene. So when we condense it, right, the mole fraction of benzene is greater than we started with. So we do the same thing again. We have more benzene and more and more and more. Keep on going. We increase the purity of the benzene that we're collecting. This is basically, this is a principle used by distillers in the distilling industry. This is a picture of they call a column still, and each of these sections right in here is what they call a plate. And in each of these chambers above each plate, this basically is happening. So it happens, all in one column. So you don't have to, this would be really tedious to boil a solution, collect the distillate, boil that distillate, all in separate steps. That would take forever, right? This does it all at once. The more columns there are, the more steps there are, more plates, the more pure the mixture, the greater the mole fraction of the more volatile component. Distillers, the more volatile component is ethanol, and water and other stuff stays behind. So depending upon the strengths of the interactions for a real solution, if the intermolecular forces between the solute and the solvent are stronger, that's AB is stronger than either the intermolecular forces between the solute and the solvent and solute, then it ends up, we get what's called a maximum boiling azeotrope. So let's talk about that. So this graph over here is showing how the boiling point of the solution changes as we increase the mole fraction of component A. And there's a maximum here. At the maximum, the the composition of the vapor and the liquid are identical. There's a tangent right there. And so that's what happens if we have stronger intermolecular forces between the solute and solvent than we have before the solute, solvent, solvent. And that makes sense, because if the intermolecular forces between the solute and the solvent are stronger, that's going to make it harder to create a vapor, and it's going to increase the boiling point. And so what we do here, okay, is we start out with a mole fraction of one of the components greater than this this mixture right here, than the composition at which the boiling point is the maximum. By the way, this mixture where when we boil it, the composition of the vapor is the same as the composition of the liquid is called an azeotrope. That's what an azeotrope is. And if you have an azeotrope and you try to boil it, you're not going to do any separation at all. You won't accomplish anything, because the gas phase will have the same composition as the liquid phase. But here we're starting out with a mixture where the mole fraction of A is greater than the azeotropic mixture. And so we boil it. What happens is here, if this is mole fraction of A, whatever component B is will vaporize. And this here, in this situation, this will be pure B. And so when we condense it and keep on going, we end up with, down here in the liquid phase, pure A, pure B up here. Now what happens is when we boil this, and what's going to happen is the second component B will vaporize until the mole fraction in the liquid, as B leaves, this mole fraction shifts, goes back over here. Once we hit this composition right here, then nothing changes, because we're at the azeotrope. The composition of the vapor is equal to the composition of the liquid. Now, if the intermolecular forces between the components, the solute and solvent, are weaker than the intermolecular forces between the solute particles with themselves and the solvent particles with themselves, then we get what's called a minimum boiling point azeotrope. And that makes sense also, because if the intermolecular forces between the solute and solvent particles are weak, then it's easier to boil the solution, and the boiling point will be lower than that of the separate components. So what happens here, okay, we start out with a mole fraction of component A less than the azeotropic composition. So we start out here, heat it up. Well, now what happens here is we get an azeotrope in the vapor phase. We don't get pure component in the vapor phase. When we condense it, we end up right here. It's drawing us right down here to the azeotropic mixture. Once you reach this mixture, it just stays. It sits right there. Now we can play with that if we use reduced pressure. So if we do the vaporization at, say, atmospheric pressure, we end up from the distillate with an azeotropic mixture. Then we take that mixture, the distillate, and put it under reduced pressure. It ends up, when you reduce the pressure above the solution, you shift the azeotrope. It goes to a lower mole fraction of one of the components. And then if we boil it here, we'll end up with what's left behind here is pure B. And that's fractional distillation.